Third part of the polycyclic aromatic hydrocarbons, we are now going to see phenanthrene. And phenanthrene is an angular isomer of anthracene. They have same number of carbon and hydrogens, only the arrangement is angular. It's not linear. It's not like this. It's not like this. It is this again. And the numbering is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Molecular formula remains the same of anthracene. It's again the same nomenclature: tricyclo 8400 tetradeca 135 7 9 11 13 heptine. Only positions are little changed. It's a pure form, it's a white granular compound just like phenanthrene. However, you see there is a considerable decrease in the melting point of almost 100 degrees compared to anthracene. Phenanthrene, if you see the structure and source, you can write phenanthrene in any way of this fashion. Either the central ring is on the top or the bottom or sideways. It's a tricyclic aromatic hydrocarbon in which 3 benzene rings are fused in angular manner. And earlier the name was derived from the composite of phenyl and anthracene. It has 5 canonical forms, and it is obtained naturally through high temperature pyrolysis of organic materials. Also during the fossil fuel, that is a moderate temperature diagenesis of sedimentary organic material to form fossil fuel, and direct biosynthesis by microbes and plants. So this is how it is naturally obtained. However, there are various syntheses also designed for phenanthrene. And first is again the Howard synthesis. As I told you, it is almost on the same lines as naphthalene, only the starting material in the case of naphthalene was benzene. Here it is naphthalene itself. Otherwise it is same succinic anhydride. The first step is Friedel-Crafts acylation using the succinic anhydride with AlCl3. Then second is of course the Clemmensen what you can say Clemmensen reduction with zinc HCl to reduce this CO group to CH2. Further dehydrative cyclization to this cyclic lactone. Again second repeated Clemmensen reduction to give you this naphthalene cyclohexane, which is then oxidized over a noble metal and warm air to phenanthrene. So this is a Howard synthesis. How are the Howard synthesis of phenanthrene and naphthalene comparable? CO2. Just say they are comparable, only the starting material is, in one case it is benzene, here it is naphthalene. Otherwise they are ditto same. I'll explain this. This happens at the alpha position. Okay, it doesn't go to the beta. Had it gone to the beta, what would have happened? It would have given again you anthracene. But alpha is more reactive in case of naphthalene, as we have studied. So this acylation will go to the alpha position. This will get reduced, and this will then further cyclize. This will cyclize, so this will hang around this one. This will again then get what you can say reduced, and this will all get oxidized. Fine. You have second total Indian scientist Bardhan Sen Gupta synthesis. It is 2 starting materials are prepared in multi-step synthesis, and then they are condensed. First is the 1 bromo 2 phenyl ethane, and this is obtained from bromobenzene through Grignard synthesis to get the alkyl magnesium bromide or aryl magnesium bromide, which is then treated with epoxide and hydrolyzed to get 2-phenylethanol, okay, which is then treated with HBr. It's a very straightforward reaction, and you get the corresponding bromide. Second starting material is 2-carbethoxycyclohexanone. So in the cyclohexanone, at the ortho position, we are incorporating carbethoxy group through diethyl oxalate. We are creating an anion here, active methylene compound with sodium methoxide, because this is active methylene compound, and then we are adding this. So one of the CO attacks with the loss of ethoxide, sodium ethoxide. So you get a type of an acetoacetate ester of cyclohexanone. This is dicarboxylated at high temperature to get 2-carbethoxycyclohexanone. Now the third step is, of course, to condense these two, and we can see here this is quite a electropositive center, a good center for nucleophilic attack. So there is a nucleophilic attack here by the bromine, and so this adds here phenyl CH2 CH2 CH2, it adds here, this is flanked here, so this adduct is formed. Now this adduct, there is a decarboxylation under using concentrated KOH and followed by acid hydrolysis. So first is what you can say, hydrolysis with KOH to COOH, and then it's decarboxylation at high temperature. So this is totally removed from here. Okay. Next step is, of course, with sodium in moist ether. This is slightly reduced to the OH, and then there is a rehydrative cyclization. This OH and H will go from here and this cyclization. So now you get a reduced type of system, which is then under selenium oxidation, it is aromatized to phenanthrene. Third is the Bogart-Cook synthesis, which is again 1-bromo-2-phenylethane. This is converted to its alkyl magnesium or aryl magnesium bromide, alkyl rather, because phenylethyl is alkyl group. And then it's treated with the ketone, so it adds there on same lines, get a Grignard adduct, dehydrated and then cyclized under a very high temperature and selenium aromatization, you get phenanthrene. So this is nicely depicted, nicely. Orientation of substitution. In phenanthrene, position 9 has lesser energy than the position 1, 2, 3, 4, as is shown here. Position 9 has lesser energy compared to these figures. So it is more prone for electrophilic attack. And oxidation is, of course, normal chromic acid oxidation first just oxidizes to the dions. Further with H2O2 you get the ring opening to dicarboxylic acid, diphenic acid. The reduction is, of course, with sodium and isopentanol. You get 9,10-dihydrophenanthrene. Halogenation, you get a dihalo, which collapses again to the 9-halo with a normal classic chlorine and carbon tetrachloride condition. Nitration also gives 9-nitro with normal nitrating mixture. Sulfonation will, of course, will not go at the 9 position, but it will go at the what you can say, the 2-phenanthrene and 3-phenanthrene sulfonic acids. Applications of phenanthrene is used in the manufacturing of dyes, plastics, pesticides, and explosives. It is a backbone for many drugs, antitussives, analgesics, antipsychotics. It's found in natural compounds, particularly alkaloids like morphine and thibin. So part of the steroidal skeleton. Rather, steroids have got the skeleton which is called as cyclopentane per hydrophenanthrene. It is a reduced phenanthrene per hydrophenanthrene fused with a cyclopentane ring system. So it is a tetracyclic ring system. Bile acids, cholesterol, and steroids. It is a skeleton. It is used in manufacturing of phenanthraquinone, which is a useful intermediate for pesticides, as well as for manufacturing of diphenyllic acid, which is a useful intermediate for resins. Here we see the two alkaloids, and here this is the phenanthrene. Here also in thibin also you see phenanthrene, and here in the steroidal nucleus you see this is phenanthrene and fused with cyclopentane, so it is called as cyclopentane per hydrophenanthrene. This phenanthraquinone, very useful intermediate for pesticide manufacture. We see some derivatives of like a diphenylmethane also, that is called as benzylbenzene, which is also commonly called as benzhydrol or a benzhydryl group. IUPAC name is 1,1-methane dibenzene. It's an organic compound consists of methane wherein 2 hydrogen atoms are replaced with 2 phenyl groups. Diphenylmethane is common skeleton in organic chemistry. The diphenylmethyl group is also called as benzhydryl group. It can be abbreviated as BZH, or it can also be called as CHPH2, and it's a part of numerous medicinal compounds and therapeutic drugs. One by one, let us see where it is. An anti-Parkinson drug, an anticholinergic drug, it is in predinol. You see this is the benzhydryl moiety. Piperidrol, this again is the skeleton. We see an antihistaminic terfenadine, fexofenadine, diphenhydramine, which is also called as Benadryl, very commonly used for cough syrup. This is cyproheptadine, and this is diphenhydramine. It is also in sertraline, which is an antidepressant compound. It is also useful in antipsychotic pimozide. These are all different antipsychotic compounds, and all these compounds which I have named here, they all have this one thing in common, and that is the benzhydryl group. So you can understand the medicinal significance. The third, another derivative is the triphenylmethane moiety, which is also called as 1,1-1-methane trial tribenzene. It's also called as a tricyl group. Triphenylmethane is a hydrocarbon, colorless solid, soluble in non-polar organic solvents and not in water. Basic skeleton of many synthetic dyes called as triarylmethane dyes. Many of them are pH indicators and some display fluorescence. A tricyl group in organic chemistry is triphenylmethyl group, pH 3C Example is triphenylmethyl chloride is tricyl chloride and triphenylmethyl radical is trityl radical. And these are some examples of triphenylmethane dyes, that is bromocresol. You can see the triphenylmethyl is a very important indicator in titration. And then in complexometric titration you come across malachite green as one of the indicator. So these are again triphenylmethane moieties. So thank you very much. I'll also supply you the question bank. Maybe in the next video I'll also give you MCQs. So thank you very much. Thank you.